Okay, so it is 7 o'clock, so we can go ahead and get started with our exam review. This is the Exam 3 review for Physics 1301. We're going over the 2016 exam today. It's linked in the description below so you can follow along, but I'll put the questions up here too. And if you have any questions from yesterday that I didn't get to answer, please let me know. I'll try to answer them if you put them in the chat window to your right. And just like yesterday, your exam 3 this time is only covering chapters 9 through 12. So there's going to be a lot of content in this packet in particular that we're not going to cover because it's chapter 13 and 14, Waves and Oscillations. That will be on your final exam. So we're going to skip those today, and I put out the numbers that we're going to skip in the description below. But you are more than welcome, and I recommend going through those when you're studying for your final, which is next week anyway. And so we are just going to go ahead and get started. So number 1 is the first one we have today. Number 1 is a gravity problem. Gravity is chapter 12, so it's the most recent thing that's going to be on the exam, but what we have here is two objects exerting a gravitational force on each other, and they have a certain magnitude of that gravitational force. And we want to see how that new force will compare if we double the masses of both objects and we double the radius between them. So what's kind of interesting is there's really only, when we went over this yesterday, there's really only one formula for the force of gravity. The force of gravity of anything is this big G, which is the giant constant number that you don't have to memorize because that is on your formula chart, times mass 1 times mass 2 divided by the radius squared, and the radius is the distance between mass 1 and mass 2. And that is the formula for the gravitational force of anything. And so it's interesting because if you were to plug in the gravitational constant, which is on your formula chart, the mass of the Earth, and the radius of the Earth squared over here, you would get 9.81 for those three terms. And that's how we get the equation force of gravity is equal to mass times gravity, because we're really just taking the mass of whatever object we're looking for times gravity, 9.81. That's where 9.81 comes from. So that's kind of cool. But here we have, in a normal sense, we have the force of gravity of these two objects is just the first mass times the second mass divided by the radius between them squared. But what we're doing now is we are looking for the force of gravity of these two objects, but now both of them doubled their masses, and the radius, or the distance between the two masses, also doubled. So the G constant, that will always stay the same. That will never change. There will never be a factor associated with G. In this universe, G is always G. But now we have 2m and 2m, because each mass is doubled. And I believe, well, it doesn't explicitly say, but I will say on your exam it will explicitly say, they want you to understand that this mass and that mass are both identical in this case. And then dividing that all by 2r squared. And we put 2r in a parentheses because it's really the quantity of the radius that we're squaring here, the quantity itself. And so before we do anything to this formula and manipulate it, we have to get rid of that parentheses right there. So 2r squared is just like saying 4r squared. So we're going to say this is g times 2m over 4r squared. We just pulled that square inside the parentheses, so it affects each term. Well, now what I can do is I see this is a factor of 2, and that's a factor of 2. And since this is algebra, so we can just multiply straight across, I'm just going to multiply 2 times 2 and take that outside, put it on the outside of this entire numerator. So it's going to be 4 times g m over 4r squared. And now what we see is we're just dividing 4 over 4. And really 4 over 4 is just 1, so that means our new gravitational force when we double both of the masses and double the radius is the exact same as what our gravitational force was initially. And so that means that F, or the force of gravity, is just F, which is answer choice A. And so this is telling us if we were to double both masses and double the radius, there would be no increase or decrease in that actual force of attraction between the two objects. It stays the exact same. Nothing there. This is more of a conceptual kind of question, but I really like gravity because there's really only one formula you have to deal with in gravity. If there are any questions, please let me know. Otherwise, we are going to move right on ahead to number 2. this. And so number 2, we have Eric holding weights in his hand, and it tells us his moment of inertia. It tells us how fast he's spinning angularly, and we want to know what is his angular speed after he changes his moment of inertia. And so the easy way to solve this problem is to realize that at any time you're spinning, I see a question. There's a lot of background static. I see a question. Let me see if I can hear that. There's a lot of background static. I do apologize, Sarah, but I personally don't have a microphone other than the one on my laptop, so I apologize that I can't fix that. I hope that's not too bothersome. But let me know. I can try talking louder if that helps. So we have Eric holding weights outstretched, and then he's going to hold his weights inwards. And so this is exactly like a problem we did yesterday, where we had a guy who held his weights out and he was spinning, and then he held his weights inward and then he was still spinning. And the key is to think about, like in a figure skater in these kinds of problems. When they hold their arms out versus when they pull them in, they start spinning faster when they move their arms in, and that's because their moment of inertia is really decreasing in a sense. Because the moment of inertia, I, for moment of inertia, is just equal to mr squared, which means your mass times the radius squared. Well, you can't change your mass. You can't change the mass of anything, but you can change the radius. And if the radius decreases and you're pulling your arms inward, that's going to decrease your moment of inertia. And we care about this in this particular problem because anytime you're spinning, and when you're in physics 1301 where the world is perfect and there's no friction, we're essentially saying that you have an angular momentum, L for angular momentum. And on your formula chart it says L is equal to I times omega. And if we remember from yesterday, that omega stands for your angular speed. It stands for the speed at which you are rotating around. And so in this class in particular, when we don't have friction in the rotational dimension, we say that L is conserved, or angular momentum is conserved. And if that's the case, we can just say our initial angular momentum is equal to our final angular momentum. And so in this case, we're just saying that I initial, omega initial, is equal to I final, omega final. And so what you should see about this is these two variables are directly proportional. And this isn't just a physics skill, this is like a life skill. When you have two numbers that are, or two variables that are multiplying together, it's an inverted proportion, which means that if one of them increases, the other one has to decrease. If one of them decreases, the other one has to increase in order to balance it out. And so in this case, it tells us that his initial moment of inertia is 5. And in case you're wondering what the units are for moment of inertia, it's kilograms meters squared. So 5, and it tells us his initial angular velocity is 3 revolutions per second. And so if you'll remember from yesterday, if you were here yesterday, we had one problem where it was in revolutions per second, but we had to convert it to radians per second. For this particular problem, I'm not going to convert from revolutions to radians per second because I look at the answer choices and I see that they're all in revolutions per second, which means you can just leave your angular speed in revolutions per second. The difference between revolutions per second and radians per second is kind of like meters per second versus like miles per hour. They both measure a speed, but they're just different quantities of a speed. So here we have 3 revolutions per second initially, and then it tells us he pulls his arms inward, so now his moment of inertia is 2 kilogram meters squared. And we know that if he's pulling his arms inward, his radius is decreasing, which means his moment of inertia is decreasing, which is why we have a lower moment of inertia here than we had initially. So right off the bat, we know that the value for our omega final has to be bigger than our initial omega, because if we're decreasing our moment of inertia, we have to increase our omega in order to balance it out, like an inverted proportion. And so this is just algebra. 5 times 3 divided by 2. You should get omega final gets you 7.5. And this is in revolutions per second. If they had asked you for the answer in radians per second, you could have converted 3 revolutions per second into radians per second and then your final answer would be in radians per second, or you can just get here and convert from here to radians per second. So just for fun, if we wanted the answer in radians per second, well, what we have is 7.5 revolutions per second, and I'm going to multiply by the conversion factor, because remember that 1 revolution in radians is 2 pi radians. So if I have 1 revolution, I'm just saying I went 2 pi radians per revolution. Well, that's just a unit conversion. Revolutions cancel out. So this would be whatever 7.5 times 2 pi is, which I'm not going to find out, but it's 2 pi times 7.5 radians per second. That's how you would convert over, if they ask you for that. And I find that for the most part on your exams, they'll ask you for answers in radians per second rather than revolutions per second. It's just more common. And so we're going to keep moving right along to number 3. So for number 3, we have another sign hanging from a wall by a bolt. And so this is almost identical to that problem we did. I think it was number 15 yesterday, where we had a sign hanging from a wall. There was a single bolt, and they asked us to find the tension of the rope that is holding up the sign. So I'm going to redraw the picture. They gave us a nice picture here, but we'll redraw it just for easier use, and we'll make it a little more defined. So there's my sign that's hanging off the wall. I'm going to say that's my bolt over there. That's the bolt that's holding up the sign. And then it tells us we have like a rope right here that's holding it up that way, and then it's hooked up over there. And it also tells us that the angle between the rope and the sign is 25 degrees. That would be this angle, 25 degrees, right there. So it tells us the sign is 3 meters long and 20 kilograms. We want to see what the tension in this rope is, because it's a rope, so it has to have tension, what it has to be in order to keep this entire system in equilibrium. And so the first thing you should do whenever you see because, well, looking at this, I see a bolt and a sign and something that might rotate, so I'm starting to think about a torque problem. I'm thinking that this has to deal with torque. And the first thing you do when you think about a torque problem is assign your pivot point. And your pivot point is the point of rotation. Everything will rotate about that pivot point. And sometimes they will be more obvious than others, but for example, this one, it's pretty obvious that they want us to pick this bolt right here as our pivot point. So if this right here becomes the pivot, that means the entire sign is rotating clockwise or counterclockwise from this pivot point right here. And so if the entire sign can rotate clockwise or counterclockwise, there has to be torques that are causing it to rotate in that direction. The obvious one is that rope right there. That rope right there is essentially a tension force. A tension force that, if you think about it, it'll rotate the system in the counterclockwise direction, right? And so if this tension force is essentially a torque in the counterclockwise direction, well, there has to be something in the clockwise direction to balance that tension force out. And what we find is that if this entire sign weighs, 20 kilograms? 20 kilograms, anytime you have a long object or an object with length, you will always assign the mass of that object to the very center of it. It's the center of mass. And just like yesterday I mentioned, for example, humans, we have a center of mass, which is our core area. That's where we would consider the very center of all of us is. You would be able to balance a human on their core area if you try hard enough. And so in this case, it tells us the entire sign is 3 meters long. So this is 3 meters in length, which means we're going to put our center of mass right about here. And we're going to say that length right there is 1.5 meters. And I get that by doing 3 divided by 2 because it's halfway through. And so this force right here is essentially the weight of the sign. And the weight of the sign is just mass times gravity, so we can substitute 20 times 9.81. And so whatever that number is, that is the weight of this sign and the force that the sign is exerting on the system. So these are the only 2 torques I have on my rotational system. The sign can either be rotated clockwise by the weight of the sign, or counterclockwise by that torque, by the torque of there. And so, well, if this entire system's in static equilibrium, the first conclusion you can say is that the sum of our torques has to be 0. When you're in static equilibrium, the sum of all of your torques has to add up to 0. And if that is the case, you can also say that the torques in your counterclockwise direction are equal to the torques in your clockwise direction. Things in rotating in opposite directions have to be equal to each other if you're in static equilibrium. And so now we can just substitute in what we know. We know that torque, I'll write it over here, torque is just equal to R times F times sine of theta. That's just our general formula for torque. And so in this case, the only torque we have in the counterclockwise direction is the torque due to tension, and the only torque we have in the clockwise direction is the torque due to the weight of the sine. So we're just going to set R sine theta equal to R sine theta. So R F sine theta is equal to R F sine theta. We just set them both equal to each other. And now we start plugging in what we know. So the radius is always the distance from your pivot point to the force in question. And so in this case, if we're talking about the tension, the force of tension, the distance from the pivot point to the actual location where the force is acting on the sine is the full length of 3 meters. And so this radius right here will be 3 meters, 3 meters. And then the force that we're looking for, well, that will just be tension, T for tension, that's what we want in this problem. And then sine theta. So this angle theta is always the angle between your radius and your force. And the easiest way to find that angle, if it's not obvious like it is here, is to put your pencil on your pivot point, draw out the radius, and draw up the force. And whatever angle you just made, that's the angle you want. So in this case, we just made that 25-degree angle. And so this would be sine of 25. And all of that is equal to the torque due to the weight of the sine. So for the weight of the sine, we said that the weight of the sine is only acting at the very center of the sine's length. And so that means the distance from our pivot point to the weight of the sine is only 1.5 meters. It's halfway down the length of the sine. So we put in 1.5 for our radius. Then our force is just the weight of the sine, which is 20 times 9.81. So we'll leave that as 20 times 9.81. I'm running out of room, but we can make it. So, and then our angle theta here, remember we just started the pivot, draw out the radius, draw out the force, and we just made a 90-degree angle. And if you remember from yesterday, well, the sine of 90 is just positive 1. So we can leave sine of 90 in here, if I didn't turn off the page, and that will just go out to positive 1. I can make it better than that. Positive 1. Sine of 90 is just positive 1. And so now, this is just an algebra equation to solve for that variable t right there. And so, simplified for the people at home, we have tension would be equal to 1.5 times 20 times 9.81, all of that divided by 3, divided by 25. And again, we have a lot of numbers here. I strongly would urge you to use lots of parentheses in your calculator rather than jamming it all in together. It's never a good idea. And so when you do all of this, you should hopefully get 232. T is equal to, can you see that? Okay. 232 Newton meters. Well, newtons. It's a tension. Tension in Newton. And so this is close enough to our answer choice that has 230. And so that is what we would pick for this one, 230. We have a comment. Could you please explain why R for the rope is 3 and not 1.5 of the... Oh, sure thing. So this R stands for radius, and radius is radius of anything is the distance from the center of your circle to the outer edge of your circle. And if you think about it, this sine, it can't really, but hypothetically, this sine would be able to rotate 360 degrees all the way around that pivot point. That's why we picked that as our pivot point, because it's the center of its rotation. And so a radius is always the distance from the pivot to the actual force. from the pivot to whatever the force is that you're looking for. So in this case, the tension of the rope is acting at the far end of the sign. And so because of that, the distance from the pivot to the far end of the sign is the full 3 meters of the sign. And then, and on the other hand, the weight of the sign, the force which is the weight of the sign, is acting here at the center of mass. And the distance from the pivot to the center of mass is halfway up the sign, which is 3 over 2, which is 1.5. Hope that makes sense. When you're looking at the radius, always find the distance from wherever your pivot is to wherever the force is. Whatever that distance is, that's what you always put in there. Cool. And so we are going to go ahead and move on to number 4, which is another rotation problem. So now we have Carol spinning on a chair with her hands in her arms. So this is another person spinning around and stretching their arms out. I have not seen your exam, but I know historically they do like to ask you questions with people stretching out their hands and pulling their hands in. And just remember, those are always inertia problems. And that will always, the conclusion you should always come to in these kinds of problems is that your inertia decreases when your radius decreases and you pull things inwards. And so in this case, we have Carol spinning in a chair with her hands in her lap, but then she's going to extend her arms out. And we want to know what's going to happen. Well, we are, this is almost exactly like problem number 2. In this case, we have her, and we're just going to draw her. There's Carol, happy to be here. And she has her hands sticking out. Those are her hands, they're sticking out. And then she decides to pull her hands inward. Still happy to be here. And so, and she's spinning in both cases. Both cases she's spinning. We want to know what's the difference here. What's the difference between these two pictures? Well, if you're spinning, you have this thing called angular momentum. And in this class, generally, you will never lose angular momentum. We're in 1301 physics, the most basic physics you will do in your life. And that just means that your initial angular momentum is equal to your final angular momentum. You won't lose any angular momentum. And the formula for this angular momentum is I omega. I, which stands for your moment of inertia, times omega, that is your angular momentum. And so we're just saying our initial moment of inertia times our initial angular speed is equal to our final moment of inertia times our final angular speed. And if you wanted to, you could get more specific because we already know for a fact that I is just equal to mr squared. So if you wanted to, you could plug in mr squared in these both i's. But what you will notice about this, if you plug this in here, the mass of Carol or the mass of you will never change. Your mass doesn't change, your radius can change, and your angular speed can change. So those are the two variables that are the most important when you're considering angular momentum. And so in this case, if she extends her arms out, I think I drew it backwards. First she had her hands inward, and then she extended her arms out. But either way, if she had her hands inward, that essentially tells us that her radius is small. And if her radius is small, we're saying that this value is little, but that value has to be big. And on the other hand, if she extends her hands outward, her radius gets bigger. And if her radius gets bigger, her moment of inertia gets bigger. So this value gets bigger, which means that our angular speed has to get smaller. And I apologize for flipping it over. But the key here is these, just like we mentioned before, these are inversely related. When one increases, the other has to decrease. When one decreases, the other has to increase. And so we know that when her arms are together, she has to have a small moment of inertia because her radius is small. And that's the same concept of like an ice skater who pulls her arms inwards when she's spinning. She's going to speed up as she pulls her arms inwards because her radius is less, which means her angular speed is more. And so in this case, the correct answer should be B, where her moment of inertia increases, but her angular speed decreases to counteract her lower moment of inertia and high angular momentum. They're inverses. They will always be the opposite of what happens to each other. So that is another conceptual question about rotation. And so in the description I also mentioned that we're skipping the problems that have to do with oscillations, waves, and simple harmonic motion, because those are chapters 13 and 14, which will not be on this exam but will be on the final. So we are actually skipping 5, 6, and 7, but I do recommend looking at those on your own when you're studying for your final next week. So we are skipping all the way over to number 8. Erase this. And so now we have another rotational problem. We have a record player, and it is slowing down uniformly. It tells us the initial speed, or the initial omega angular speed it had, and the final angular momentum or speed it had, and the displacement in radians. We want to find angular acceleration. So they gave us a few terms. They tell us the initial angular speed, which is 25, and we'll leave the units in there, radians per second. They tell us the final angular speed, which is 13.5, and again, that is in radians per second. And they also tell us a certain displacement. And I don't know if they emphasize this enough in class, but when we were talking about, well, if we're talking about this distance in general, we usually measure that in meters. And so in kind of the same format, when we're talking about distance with a circle, I remember when I first took physics, they actually, the distance is really the arc length, the arc length of the circle. That is your distance. And if the letter for that was S, I don't know if they do that in your class anymore, but it was S for arc length. And arc length is measured in radians. That's actually where we get the 2 pi radians from. That's the arc length of a full 360-degree circle. And so in this case, they gave us an arc length in radians. They told us the displacement, and I'm going to use S for displacement. That's not the number 5, that's the letter S, as 14 radians. So that's usually symbolized as rad for radians. I personally don't recommend you use, like they told you displacement, I don't recommend you use the letter D for displacement, because it'll often get you confused with E for meters, and you might get your units mixed up, especially in a multiple part problem. Personally, if you don't like S, feel free to use another letter. I just wouldn't use D for this. So what we have here is an initial speed, a final speed, and a displacement, an arc length. And they also tell us, which is kind of interesting, they gave you a hint, they said it slows down uniformly. So if it is slowing down from 25 to 13.5 uniformly, that means it has to have an alpha, an angular acceleration, a constant angular acceleration, and so more so that it has to have a negative angular acceleration because it is slowing down. And so what I'm starting to think about is, well, if we have alpha, we're talking about acceleration, we're talking about maybe kinematics, or rotational kinematics, since we have rotational terms here. Well, one of our kinematic equations, I think it's the second one, it says that omega final squared is equal to omega initial squared plus 2 times alpha times arc length. And that's an S for arc length, or whatever you prefer for radial distance. And so now we have everything we need to solve for that alpha term right there. That's all we need. So our final speed is 13.5 radians per second squared is equal to our initial speed, which is 25 radians per second squared, plus 2 times alpha, which is what we want in this problem, times our radial distance, which is 14 radians. 14 radians. And so notice how you can just leave 14 radians in here and you don't have to convert it to anything. Sometimes, and I will say this, sometimes they might give you like degrees. They might tell you that instead of an arc length that it went through, they might say the record spun a total of 90 degrees. And if a record spun 90 degrees, that's like saying it went a quarter of the way through the circle, and from your pre-calc class, I hope you know that that is pi over 2 radians. And then a full half a circle would be pi, 3 pi over 2, and then 2 pi. it's great to know your unit circle. You won't be tested directly on it, but they might give you degrees and expect you to know how many radians that are, just the easy ones, like 90, 180, 270, and 360. So in this case, this is just algebra to solve for alpha. You should hopefully get alpha is equal to negative 15.8, but they only ask you for the magnitude of acceleration, which means they only want the positive value of that. And by the way, at angular acceleration, alpha is measured in radians per second squared in a similar manner to how linear acceleration is measured. So not much difference there. And so your answer choice should be A, 15.8. That's the closest one. So another great example of rotational motion. We're going to go ahead and move over to number 9. And so now, another rotational question, but now we're kind of bringing torque into this. So we have a blender with and it gives us a moment of inertia, and it accelerates at a uniform rate, and we want to find the rotational kinetic energy after a certain amount of time. So in this problem, what they give us, first of all, is that its moment of inertia, I, is equal to 7 kilogram meter squared. That's its moment of inertia. It also tells us that it has a torque that is constant at 3 Newton meters. And Newton meters are just our units for torque. Also, it tells us that it's starting from rest. And if we're talking about something that rotates and starts from rest, we don't use V for velocity. We use, just like we did in the last one, omega. Omega initial is 0. It starts from rest. And it also tells us, one last thing, it tells us that the time that it spins, or that it's blending, is 5 seconds. And we want to know its rotational kinetic energy. Well, so yesterday we had a couple of really good examples of our rotational kinetic energy. Something to remember, though, is our formula for kinetic energy rotation is equal to 1/2 I times omega squared. So in this case, well, we want to know what our rotational kinetic energy is. We know what I is, but we don't know what omega is, omega being the speed. We know the initial speed of this blender, but we don't know the final speed of this blender. We have to do something to figure that out. So what if we were to maybe manipulate because what I'm thinking of right now is that if we wanted to use a kinematic equation, we usually need an initial speed, a final speed, and an acceleration for almost all of our kinematic formulas. Well, all we have is an initial speed. We don't have a final speed. We don't have an acceleration. But there is another way we can get acceleration. We talked about this a little bit yesterday. We said that torque, another formula for torque that's not the easy one, that's RF sine beta, is that torque is equal to I alpha. Torque is equal to your moment of inertia times your angular acceleration, and that is a constant fact. And so we know what our torque is, and we know what our moment of inertia is. So in that case, we can say 3 is equal to 7 times alpha, and we can find alpha. And the reason we want alpha is in order to find our final speed by using maybe a kinematic formula with the other information we have. So this would just be 3 over 7 is equal to alpha, which I think is 0.43, 0.43, and that's radians per second squared. So that's our alpha for this problem. And so now what we need is our omega final. And remember, we're finding this omega final because in order to find rotational kinetic energy, we have inertia, but we need our speed that we're rotating, and we can't just put 0 in there. So a kinematic formula that I remember is omega final is equal to omega initial plus alpha t. And that's the exact same as our linear kinematic formula that says v at final is equal to v initial plus acceleration times time. It's the same concept, we just switched out the variables. So in this case, we are looking for omega final. We know our initial omega, our initial speed is 0. Alpha, we just found to be 0.43, 0.43, and we know the amount of time it spends spinning is 5 seconds. And so to put that in your calculator and get omega final should be something around 2.1 radians per second, or close to that. So we're not done yet, because we don't just want our final angular speed, we want our rotational kinetic energy. And in order to find that, we have to multiply the square of this times inertia and divide by 2. So we're going to say kinetic energy of rotation is equal to 1/2, that's a constant, times I, our moment of inertia, which they told us is 7, times our omega squared, so times 2.1 squared. And then that's just plug and play in your calculator. You should hopefully get 16-ish. 16 joules. And I know that the unit is joules. You don't have to multiply this out to get joules, but I know it's joules because kinetic energy is an energy. And just like we learned in Unit 2 for Exam 2, all energy is measured in the unit joules, J for joules. And that should be good for number 9. And again, if you have questions, please do let me know. Otherwise, we are going to skip number 10, because number 10 is an oscillation problem, which is a good final exam practice. And we're going to do number 11. Actually, we're gonna skip 11. Eleven is a problem that we're going to get to, but I will do that at the very end, and for a reason that I will explain at the very end. So we're going to do 12 and the rest of the packet, and then we're going to come back to 11. Up there. And so now we have another gravity problem. It tells us the acceleration because of gravity is decreasing, that a further away an object is from a surface. Well, logically that makes sense, right? The further away you are from Earth, the less there is gravity, right? That's why if a spaceship goes far enough, they will be in space and not be pulled back to Earth by Earth's gravitational force. And so it tells us at what height above the Earth's surface do we experience an acceleration due to gravity of that specific amount, 0.54 g. And notice that it says 0.54 lowercase g, and so that's referring to our gravity, which is 9.81. So it's saying, where above the Earth do we feel a gravity of about half of 9.81, about half of what we normally feel? And they give us some constants. And I like that they gave us the constants. It's a good example because on your exam, you don't have to memorize what the mass of the Earth is or the radius here. It'll always be given to you in some way or the other. Whether it's on your formula chart or elsewhere, you don't have to memorize that. And so a good formula to know is the acceleration due to gravity of anything. Acceleration due to gravity of anything is equal to big G times m over, I think it's r squared. And you might be wondering, that formula looks very familiar to the very first formula from this packet we did today. And it is, because that first formula said that the force due to gravity is equal to big G times m times another m over r squared. Well, you'll notice the only difference between that and that is there's an additional mass attached there. And that's really because all forces on Earth, well, in our universe, are equal to mass times acceleration. So if acceleration due to gravity is this, if you multiply it by a mass, like we do here, we have another force. And that's where that comes from. It's all coming together now. And so we're saying that we want to find where, at what height, that we would find 0.54 of our gravity. So we know that our gravity is 9.81. But we don't want 9.81, we want 0.54 times 9.81. We want about half of whatever our gravity is. So we want to find what height above Earth. So really, we're looking for that radial distance, because that radial distance is the distance from the core of the Earth to whatever height or whatever distance from the Earth we need to be. And so, G is a constant, that doesn't change, and I'm actually going to put in the value for G. It's a giant number, which they do tell you, 6.67 e negative 11, which just means times 10 to the negative 11. And then we have the mass, and remember that mass would just be mass of the Earth. And you might be wondering, well, if we're talking about what height do I have to be in order to in order to experience this level of gravity, doesn't that involve my mass as well? Well, your mass, well, let's think about it. It says the mass of the Earth is 6 times 10 to the 24th. Your mass is probably somewhere in like the 100 kilograms or so. 10 to the 24th, 100 kilograms. Your mass is essentially negligible in this situation because we are so much less massive than Earth is. So in this case, we only care about the mass of the Earth, the mass of the planet. So that would be, to be specific, 5.97 E24. You could round that to 6 instead of 5.97. You'll get close enough with your answer that it wouldn't matter. Divided by, and now this is where it gets interesting. I'm not going to put in the radius of the Earth. I'm going to leave it as r squared, and I'm going to try to solve for r. And the reason for that is this value of r that we get here, I'm guaranteeing you right now that it will not be the radius of the Earth value of 6.38 times 10 to the 6th. That's listed in our problem. It will not. It will actually be, I'm assuming, a number that is, well, we're not going to speculate, but it is not going to be that value in particular. And the reason for that is because we are doing gravity times 0.54. If you were to get rid of this 0.54 and you did that entire equation as it is, that radius would be the radius of the Earth, and that's exactly how we get the value of 9.81 as gravity for Earth. And it's super interesting because Isaac Newton figured that number out without calculus or without actually knowing how much the Earth weighs, which is super cool. If you guys are into that kind of thing, please read up on it. So this formula, do that to find your radius. And to find radius, you would just, where is it over here? R is equal to 6.67 e negative 11 times 5.97 e 24 divided by 0.54 times 9.81, and then take the square root of all of that. And again, I strongly recommend using tons of parentheses in your calculator. They will get super jumbled up when we get numbers as big as like times 10 to the negative 11th or 10 to the 24th. So when you do all of that, you should hopefully get R is equal to 8.67 E6 meters. And so you might be wondering, well, that is not one of the answer choices. That is not any of my answer choices. Well, the reason for that is because if we are experiencing less than gravity, right, 0.54 is less than full gravity, you would expect that we would not be on the surface of the Earth, but rather we would be maybe a little bit out into the atmosphere. We'd be a little farther away from Earth, but definitely not at the surface of the Earth. And so we'll draw a little crude diagram right here. If that is our Earth, if that is our planet, and we'll say that is Texas, where we are right now. There's Texas. There's Houston. Right there. There we are, right there on the surface of the Earth. And what is happening here is the Earth, the distance from the center of the Earth to the surface of the Earth, that distance is what they tell us. They tell us the radius of the Earth is 6.38 E6. 6.38 times 10 to the 6th, and that's meters. Well, what we found is that the distance that you'd have to be in order to experience about half of gravity is 8.67 times 10 to the 6th. So that means we have to be farther away than the surface of the Earth, the distance to the surface of the Earth. So we're maybe, I don't know, let's speculate, we're maybe somewhere out here. We're saying that that entire distance is 8.67, well, E6 meters. We're saying that whole distance is 8.67 times 10 to the 6th meters. So we want to find what is this distance right here, because that distance right there is the distance from the surface of the Earth to wherever we're experiencing gravity at 0.54 times 9.81. And so to do that, it's just subtraction. We're just saying 8.67 E6 minus 6.38 E6, and cool trick. If you're dividing, I mean, you have calculators, you don't need to know this, but if you're subtracting two values that have the same exponent, you can pretty much just ignore the exponent and subtract these two. So you should get, I don't think you can see down there, so I'll do it up here. You should get 2.2 0.29, and still E6. That E6 doesn't change when you're subtracting things with the same exponent. So, and so you also might be wondering, well, we just found meters, but our answer choices are all in kilometers. Well, meters into kilometers, hopefully by this point in the class you know that there are 1,000 meters in 1 kilometer. So we would just be dividing this by 1,000, which is dividing by 10 to the third, which essentially means we have 2.29 E3 kilometers. And if you put that in your calculator to get a full value, that should be about 2,300. It would be I'm running out of room here. Don't worry. It would be 2290 kilometers would be your final answer. And you'll find that with a lot of these problems that have to deal with gravity, where we have these giant numbers, there's a ton of rounding involved with them. So if you end up rounding in your problem, it's not a big deal. You'll get close enough to your answer anyway. But yeah, this is a very good example of something you might get in your exam. And if there's no questions, we're going to move ahead to number. We're skipping 13 because 13 is about a pendulum and simple harmonic motion, which is not on this exam. And we're doing 14, and then after 14 we're coming back to number 11. So, number 14. Now this is a conceptual question, which you can't expect on your exam. We are comparing translational kinetic energy to rotational kinetic energy of a circular hoop. And so whenever you get a problem that asks about something like translational kinetic energy, that's really just asking about normal kinetic energy. It says Ke is equal to 1/2 mc squared. Translational is your regular linear kinetic energy. Rotational, on the other hand, that is kinetic energy is equal to 1/2 I times omega squared. It is always that. And remember that when you're dealing with rotational kinetic energy, that I has the ability to change into whatever it is for the shape. And I will bring up the example that I used yesterday. Right here I have a roll of paper towels, and then I also have a roll of Clorox wipes. Both are cylinders, really, but one has a hole in the middle and one does not. And so even though they're both cylinders, they have different moments of inertia. Depending on your shape, you have a different moment of inertia, but it'll always, and that's why I always write I is equal to mr squared, it will always be some variation of mr squared. It will be some fraction of mr squared. And what I don't like about this problem, and what I can guarantee on your exam that you will get, is if you were to get something like this, which is, it's saying a circular hoop, so it's like a circular hoop that's rolling, they will tell you what the moment of inertia is. They won't make you have to guess or have to memorize what that is. And I will tell you, for this problem, I is equal to mr squared. This is, a circular hoop is the most rollable device on the planet, really. And if you don't believe me, feel free to pull aside things in your house that are circular hoops versus solid hoops and see how fast they roll down a hill or something, if you have free time. It's a lot of fun. So, in this case, we have I is equal to mr squared. So we're trying to find we're trying to find if the energy is different between kinetic energy and kinetic energy of rotation, how these two energies compare. So for this energy, well, all it really is 1/2 the mass times the velocity squared. We don't know the mass, we don't know the velocity, so we'll leave it as that for now. But for this one, well, it's I omega squared, but we can go ahead and plug in this mr squared for that I. So I'm going to say Ke, and I should be specifying Ke rotation is equal to 1/2 mr squared omega squared. And again, we're going to do the exact same thing we did the other day with making that distinction that omega, I'll write it over here, omega is the same thing as saying translational velocity over r. That's on your formula chart. I think on your formula chart it's v is equal to omega r, but these are the same formula. You just moved it around a little bit. So knowing that property, omega is equal to v over r, we can plug that in right here. So this becomes 1/2 mr r squared v squared over r squared, right? Because v over r squared is just the same as distributing that squared in between these two objects. And what I want to do is, now that I see a r squared and an r squared, well, I can just cross them both out. We don't need them anymore. And all we're left with is 1/2 mv squared. Well, it looks like that 1/2 mv squared is the exact same as that 1/2 mv squared. And it's true that whenever your moment of inertia is mr squared, your translational and your rotational kinetic energies will always be identical. And if you don't believe me, we did a problem exactly like this yesterday, where we found that we could say 1/2 v squared plus 1/2 v squared is equal to our full velocity. I think that was number 13 from yesterday, so please feel free to review that one. But this, whenever you have a hoop, something with a moment of inertia of just mr squared, that's when your translational and your rotational kinetic energies will always be identical. So your answer should be E. They are both equal. Should be E. They're equal. And so, you might be thinking, are we done yet? We are not. We have to go back to number 11. And so, number 11 is my least favorite problem from this entire packet because I do not like the way it was written. And again, if you didn't get my disclaimer from yesterday, these are not official problems that are put on exams. In fact, I don't think any of these problems have ever been on an exam before, anything similar, anything directly like these. So these were all written by students who have previously taken this exam and kind of recall how they experienced the exams. And so this is probably one of my least favorite problems out of all of the packets that I do in these review sessions. So it tells us there is a satellite that is launched towards the sun, and we want to find the distance from Earth that the gravitational force from the sun and the Earth cancel out the satellite, and they tell us a bunch of different values. We want to see where the gravitational forces cancel each other out. So first step to this is kind of draw it out because it's a little hard to visualize. So we're going to say that is the sun. Make sure to give it rays because it's the sun. There's our sun. And then we're going to say over maybe about here, it's smaller than the sun. We're going to call that Earth. Make sure to draw out Texas. There's Texas. We're not even going to call it Earth. We're going to call it Texas. And so we say that we have a satellite that's somewhere in between the sun and the Earth. We're going to say the satellite is somewhere about here. Doesn't matter where you draw it. Make sure to give it wings. That's our satellite. Whatever you want to draw it as. And so we want to find what is the distance from the satellite to the what is the distance from the Earth that where the satellite force will be zero, essentially, because whenever if you yourself are in space, you are never not being acted on by any forces, even though you are essentially in zero G, zero gravity. So this satellite is being attracted or pulled by the Earth, but at the same time it is being attracted and pulled by the sun. And if you don't believe that the sun's attraction is that powerful, well, we have 8 planets in our solar system that keep rotating around the sun because of the gravity of the sun. So we want to find this distance right here. We want that distance. D equals question mark. We want to know what that distance from the Earth to the spaceship is, that essentially the sum of all of our forces is equal to 0. Because we want them to cancel out, meaning the sum of our forces is 0. So what they do tell us is the mass of the Earth and the mass of the sun, which are two giant numbers, by the way, and they also tell us the distance here. They tell us the distance between the sun and the Earth. They tell us that entire distance is 1.5 times 10 to the 11th meters. So a giant number, 1.5 d11 meters. And so I'd say the setup of this problem is the issue with this problem, because we're saying that the forces cancel each other out, so that the force between the sun and the spaceship is the exact same as the force between the Earth and the spaceship. They have to be equal. So we're saying that the force due to gravity of the, and we're going to get a little messy here, but sun slash SS for sun slash spaceship is equal to the force due to gravity of the Earth slash spaceship. We're saying the gravitational force of attraction between the sun and the spaceship is equivalent to the gravitational force of attraction between the Earth and the spaceship, which is a little weird to think about. But so we can expand this a little more because we know the F gravitational formula, and we'll do it over here. F gravitation is equal to G times M1 M2 over R squared. That's on your formula chart. So we can put that formula in right here. We can say that the force of gravity of the sun and the spaceship is equal to G times the mass of the sun times the mass of the spaceship over the radius squared. And that radius would be the radius between the sun and the spaceship. It would be the distance, really, between the core of the sun and the core of the spaceship. And so this exact same thing we can say happens on the other side of the equation. We can say that the gravitational force between the Earth and the spaceship is just G times the mass of the Earth times the mass of the spaceship divided by the radius of the, well, and this would be the radius of the Earth slash spaceship squared. It would be the distance between the Earth and the spaceship squared. So you can see how this problem is getting a little intricate, but we'll keep going. So what I also noticed about this problem is on both sides of this equation, I have the big letter G, and G is the gravitational constant for our entire universe. So regardless of if we're talking about Earth or the sun, G is the same. And so if it's the same, we can just cross it out because it'll just divide itself out anyway. And you'll notice they didn't even give you G in this problem because you don't need to know it. And you'll also notice that they didn't tell you what the mass of the spaceship is. Well, because it's on both sides of our equation, and so that means we can just cross it out. And so now we're left with something that's a little bit more manageable. So what we have left, and I'll do it over here, we're left with, and we'll draw a little line right there, the mass of the sun divided by the radius, and I'm just going to leave the radius of the sun squared, is equal to the mass of the Earth over the radius of the Earth squared. And so, it's a little lopsided, but so you'll notice that they gave us the mass of the sun and they gave us the mass of the Earth. So we know the mass of the sun and we know the mass of the Earth. But what we don't know is that this radius is the distance from the sun to the spaceship, and this radius is the distance from the Earth to the spaceship. And we're really looking for this value right here. We want to know what the radius of the Earth to the spaceship is. Well, we can do a little bit of manipulation to get us a little closer to what we want, because what we do know is the mass of the sun and the Earth. So what I'm going to do is, if you remember from way back in elementary school, the butterfly method of multiplication, where we cross-multiply these two values. So I'm going to cross the mass of the Earth over and then cross the sun over. So this equation is going to look like mass of the sun over the mass of the Earth is equal to the radius of the sun squared over the radius of the Earth squared. And so now at least we know one side of the equation. We can substitute in and find a common factor right here. And so this common factor would, and please this color, I think you can see over here. So mass of the sun, they tell us, is 1.5 E11. So 1.5 E11 divided by the mass of the Earth, which they tell us is, oh, that is not, I apologize, it is not 1.5 E11. That is the distance between the sun and the Earth. They tell us the mass of the sun is 1.99 E30, which is a giant value, by the way. Then we have divided by 5.97 E24, which is much less than the mass of the sun, and all of that's equal to radius of the sun squared over radius of the Earth squared. And so if you were to figure that out, you should hopefully get, and let me see if I got this right. And one more thing that I wrote in my notes that you should be doing is if we have radius of the sun squared over radius of the Earth squared, that's kind of the equivalent of us saying radius of the sun over radius of the Earth, and in giant parentheses, squared. And so if that's what we're saying, then we could just take the square root of this entire side of the equation and get rid of that square right there. So it's kind of a little bit of algebraic manipulation. And so if you do all of that, you should hopefully get the ratio of the radius of the sun over the radius of the Earth should be equal to, and I got 577. And this is where the issue comes in with this problem. You just found a ratio of the distance between the sun, the spaceship, and the Earth and the spaceship. And so from now, there is no other way to solve this problem from 577 other than to plug in your answer choices, which personally, I don't like that method of plugging in your answer choices, because that just really doesn't tell if you learned something from this. So since we're going to essentially say that the radius of the sun, and we'll mark it out here, this distance would be our sun, and this distance would be our Earth. And we're saying that the ratio of that distance divided by that distance is 577. And so if we were to use answer choice, let's say we use answer choice A, which is 2.6 times 10 to the 8th meter. We're essentially saying that because the answers are what the radius of the Earth is. The answers are what the distance is from the Earth. So we're saying that this value here would be 2.6 times 10 to the 8th. So if we were to, I think you can see down here. So we're saying our sun over 2.6 E8, 2.6 times 10 to the 8th is equal to 577. And now it's just checking if you're right, because what we do know for sure is that the entire distance here is 1.5 times 10 to the 11th. So if this distance right here, our Earth, is 2.6 E8, well then we just take 1.5 E11 and subtract away 2.6 E8 to get us our sun. And if you do that, you should hopefully get that our sun is equal to, you can put that on my page. I did not, so I'll pull out my calculator and figure it out for us. So if we were to do, and using parentheses, 1.5 E11 and subtract away 2.6 E8, we get, this value should be 1.49 E11. And the reason I wanted to find that value is because now we have to check if this equation is correct. So if this is correct, if we were to plug in 1.49 E11 right there for our sun, we should get 577. Now what you'll find is when you do plug those in, 1.49 E11 over 2.6 E8, you do get roughly 576-ish, which is very close enough to be the right answer. And so the reason I don't like this answer is because if I was the one who wrote this question, I would stop right here. I would ask for the ratio between the sun, the radius to the sun, and the radius to the Earth, and I wouldn't ask you to find the actual value of either of these distances, because it's too hard to if you are given more information than what they gave you. But hopefully you can see why I don't like this question. But either way, I don't think you would get something as intricate as this on your exam, but this is great practice for knowing the material inside and out. And I think my stream froze. Great. Okay, well, other than that, that is all I had for you today. All of the other problems on the packet are great practice, but they are dealing with Chapter 13 and 14, which are on the final, so please do go over those if you need the extra help. Otherwise, I appreciate you guys coming out today, and good luck with your exam. Also, before you leave, on Monday the 27th, which is this upcoming Monday, we are having a final exam review. It is not here on this YouTube channel, it's on Microsoft Teams. The link to that is on my Physics Friends website where you found the exam review. So please feel free to come to that if you need extra help. It'll be myself and my friend Taylor will be teaching with us. So So thank you guys for coming out. I will stick around for questions for a few minutes and then I'll end the stream.